This is my lab 4 submission for Physics 2211, Physics 1. My name is Shafi. Let's get started. So the purpose of this lab is just to investigate the motion of a spring mass system. That's to say that we have mass that's oscillating in an arc. We're going to use Tracker to track the observed position. I've coded a computational model using using some of the code that they provided using GlowScript. The goal that we have here today is just to determine if the energy principle is being followed and also get some general idea about the differences between the predicted motion and the motion that we actually get observed. So what are the physics principles behind this lab? First of all, of course, as with every lab, to be honest, we have Newton's second law. That's just to say that the system's change in momentum is proportional to the net force applied. And second of all, we have the energy principle. That's to say that the change in energy is the sum of work done by surroundings and thermal energy exchanged with the surroundings. So this looks like the kinetic energy equations, Hooke's law, the spring energy, stuff like that, right? I'll get into the formulas in the next slide. Thirdly, right, just some general update formula, the velocity update formula that we've derived from the second law. We've seen this in previous labs as well. So this is just some of the formulas that we have. You can see the different formulas for the energy principle, UG, US, uh, okay, mgy, mgh for the gravity equation, y just being meaning the y coordinate here. That would be your height, right? And half ks squared. Some people call it half kx squared. That doesn't really matter, but that's the kinetic equation energy using Hooke's law, right? And half mv squared. That's just your regular kinetic energy equation, right? Here we have like our net force formulas or velocity update formulas, just the generics, the usual stuff, right, that we've seen, and our FNet formula, of course. And this is generally what we're going to use for this experiment. Briefly, if we go over like our results, right, we generally find that the energy principle holds. That's to say that this adds up to zero. There are some minor discrepancies between the predicted model and the observed data that we have here. You can see the blue and the red, and we'll get into that when we actually talk about the results in detail. The initial conditions are just our system is a spring, mass, and the Earth. Our surroundings are technically nothing but like damping sources like air resistance, which you'd otherwise assume to be negligible for simulation, might hamper the experiment. And again, I'll get into that later, right? This is the initial position vector that we're starting with. This is just based on like the values I got from tracker calibration. The mass of the ball is fixed and at 0.402 kg, and the initial velocity is just 0.000. Since we're starting from rest. This is the experiment being like done in tracked and tracker. You can see like so we have a vague idea of the graphs here to the right. Nothing too interesting here, to be honest. Oops. Uh, yeah, this is how we did the experiment and tracked it in tracker, basically. And now for our computational model, right? This is on the left here. We just have some initial assumptions that I took, well, not assumptions, but like generally the initial conditions that we have based on the experiment. So the ball position, that's based on the tracker values, ball velocity 0.000. These are just some constants. And now here we have sort of the equation to calculate our different kinds of energy. So UG, US, kinetic energy, and the total energy, right? You get the idea. The length and orientation of the ball as well. Now this is the big like important part. Right? This is like our iterative loop in order to make sure that we're tracking our motion effectively, right? So we have a delta, we have a cap value, a ceiling value for t that y is less than 9.4. We'll keep doing this over and over, and we also have a value for delta t. I don't think I included it here, but it's 1 over 120. That's what I used. And basically using this value, we're just iteratively applying this loop over and over and over again in order to get the position of the ball, a model at least of what the position of the ball should be, right? And I used a pretty small delta t, that's 1 over 120 again, just so that it's a bit more accurate. Of course, that's not 100% accuracy, but like, yeah, the iterative model is a bit more accurate with a smaller time. And so the results that we got, first of all, the energy results that we got, the total energy of the system is zero when adding the spring, gravitational, and kinetic energies together. Hence, we find that no work is done by the surroundings, and so the energy principle holds here. So that part of the experiment we've shown to be true. And now for the predicted versus observed motion, right? This x position versus time to the left, y position versus time to the left. We can see that generally, right, they follow a pretty similar path. I guess you can see like a trend that like as the experiment goes on, they deviate further and further, and that might be due to potential differences in the environment, errors like air resistance, etc. That I'm going to get into here, right? So possible sources for this deviation that we see here in the result. First of all, air resistance, friction, external factors like wind and temperature, which we considered negligible for the simulation, but might have had an impact on the result. Generally, approximation errors, right, like iteration and time steps in the computational model, which could result in inaccuracies. So the bigger the time step, the more the inaccuracy, right? Although I use a pretty small time step, there is still the potential for inaccuracy, right? And then lastly, of course, manual tracking and tracker. There's always the potential for human error, right? And finally, for the what does this mean questions, is the energy principle satisfied? Yes. The energy of the system is the same throughout the entire motion. The total energy always equals zero. No work is done by the surroundings, and we showed this in the results screen as well. Now for the difference between the periods of oscillation, right? The x position basis is 1.581 seconds, and the y position basis is 1.424 seconds. Just taking two random points, right? And like defining the period of oscillation from there. You're doing some math. The difference we get there is about 0.15 seconds, right? I hope this experiment was sort of helpful for you, and the results were satisfactory. Thank you very much for watching. Have a good day.